Hi, Assalamualaikum warahmatullahi wabarakatuh and have a blessed day. My name is Nurhidayatul Aisyah binti Azaman from AS245. Today, I am honored to present my final year project which focuses on the potential of Chlorella vulgaris, a microalgae species, to sequester carbon dioxide through its cultivation in a batch of photobioreactor. This research is the part of my undergraduate studies at the Faculty of Applied Science majoring in Applied Chemistry under Madam Nurjana binti Yuri, which is my supervisor. The research background for this project are finding the ability of Chlorella vulgaris to reduce carbon dioxide by carbon fixation to treat the air pollution and simultaneously produce the maximum biomass. The analysis of advanced method used in measuring carbon content that Chlorella vulgaris will absorb. Find the best condition that maximizes the growth of Chlorella vulgaris in pH and effect of concentration of nutrient which compose fertilizers. For the problem statement are how to measure the carbon fixation that absorbed by Chlorella vulgaris, how many days will Chlorella vulgaris growth take in a batch photobioreactor, what is the optimum condition that we'll need for Chlorella vulgaris to grow in a huge quantity. Lastly, for the introduction part is the significance of the study. Can Chlorella vulgaris be utilized to reduce carbon dioxide and treat air pollution through carbon fixation? Then we go to the objective. From this project, there are two objectives which are to study the optimum condition for maximizing Chlorella vulgaris growth rate using different concentration of nutrients, which is compost fertilizers, and to evaluate the carbon content in dry biomass. The picture shows the carbon fixation by microalgae. The production of biodiesel from algae biomass as a renewable source took a great interest in recent years. Algae biomass can produce oil more than the rest of biodiesel feedstocks such as soybean, corn, rapeseed, oil palm, and yellow grease per unit of growing area, as well as algae can provide different types of renewable biomass such as proteins and lipids. As carbohydrate, microalgae are microorganisms that can grow via photosynthesis process. It converts light, water, and carbon dioxide into biomass typically found in freshwater and marine systems. Microalgae reproduction occurs primarily by vegetative asexual cell division. Microalgal carbon capture has also several advantages over trees, such as higher photosynthesis rate, clean and low-cost technology, and production of various high-value co-products like biodiesel, pigments with medicinal values, animal feed for aquaculture, biomass, fertilizers, and other cosmetic products. One of the most significant applications of algae in reducing carbon dioxide emission lies in the production of biofuels. Algae-based biofuel, also known as green crude, have gained traction as a potential carbon-neutral alternative to fossil fuels. When algae are cultivated for biofuel production, they absorb carbon dioxide from the atmosphere during photosynthesis, converting it into organic matter. This process sequesters carbon dioxide effectively, reducing its presence in the atmosphere. Algae's carbon capture capabilities extend beyond natural ecosystems. Various industries such as wastewater treatment, plants, and biogas facilities can benefit from utilizing algae to capture carbon dioxide from their processes. Algae provide an eco-friendly and cost-effective solution for recycling carbon dioxide emissions, as they require minimal resources and produce valuable biomass, which can find application in various sectors. From the outer named Coronadorius, it shows the morphology of Chlorella vulgaris. Chlorella vulgaris has spherical shape, and when the cell in a state of death and the cell wall get affected, the species will change colors to dark green. The habitat for Chlorella vulgaris is in fresh water or in a lake. To be specific, the vigorous mixing induced by aeration of carbon dioxide enriched gas bubbles could lead to internal flow of microalgal suspension and prevent cells settling to the bottom, and adhering to the walls of photobioreactors. The mixing of nutrients and microalgae cells with the internal flow ensures the uniform distribution of nutrients to the cell and high microalgae growth rates. Besides, the mixing also guarantees that all microalgal cells could be equally exposed to the light energy, hence enhancing carbon dioxide molecules transfer from the bubbles to inside of microalgal cell. Algae bioreactors can be placed near carbon dioxide, allowing direct capture of the greenhouse gas before it enters the atmosphere. By combining these bioreactors, we can reduce carbon emissions and make useful biomass or biofuels. And the two-phase flow can also take away the oxygen and heat released by maintaining suitable pH at 3 and temperature about 15 to 26 degrees Celsius in the photobioreactor for microalgae growth. Light is an independent power for microalgae photosynthesis. Absorbing and transferring of light in the microalgae suspension is the key factors affecting the photosynthesis rate directly. Therefore, an efficient photobioreactor should be able to harvest as much light energy as possible and then transport and distribute it into microalgae cells in suspension so that maximum light energy can be used for biomass accumulation. However, in fact, a typical photobioreactor can be treated as a three-phase system. The culture medium, algae cells, and carbon dioxide bubble are considered as liquid, solid, and gas phase respectively. According to the Ultima, it stated that Chlorella vulgaris optimum growth at pH 3. This can be proven from the graph that plotted. The plot shows that the line of the highest is at pH 3. For the concentration of nutrient, which use compost fertilizer by Alter Amar, the cultivation of Chlorella vulgaris in different concentrations of nutrient which use compost fertilizer. The graph shows that the growth curves of 80 mg per liter give the optimum growth of Chlorella vulgaris. This shows that the factor affecting growth of Chlorella vulgaris are effect of pH and the concentration of nutrients. Next, the elemental analyzer result that show the composition of carbon, nitrogen, sulfur, and oxygen. The value of elemental analyzer is stated by Alter Adam. Firstly, the preparation of nutrient for Chlorella vulgaris. 50 g of compost fertilizer was weighed. 900 ml water in 1 liter conical flask stirred for 24 hours using magnetic stirrer. Next, the cultivation of Chlorella vulgaris using Doron bottle as photobioreactor, 500 ml seed and 50 ml nutrient, and top up the remaining bottle with tap water. The room temperature at pH 3, photo period 24:0 light dark cycle. For the measurement of growth Chlorella vulgaris, 20 ml sample pipetted out and using UV spectrometer at wavelength 540 nanometers. Next, we go to the pH adjustment using 1.0 mol of hydrochloric acid to adjust pH using pH meter to get the pH optimum, which is pH 3. The biomass collection and harvesting microalgae. Dry the sample in the oven for 70 degrees overnight. For the harvesting of Chlorella vulgaris, 5 g alum sulfate is added and the pH was adjusted to 12. Biomass was dried in oven in 70 degrees overnight. The cultivation with different concentration of nutrient was cultivated in 1 liter bottle at the same condition but different in volume of nutrients, which are A, B, C, D. A 10 ml of nutrient, B 20 ml of nutrients, C 30 ml of nutrients, while D 40 ml of nutrients. For the ash content, dry biomass of algae was put in the crucible and weighed the crucible, then put into the furnace. The temperature used was 550 degrees Celsius, RAM 15 degrees Celsius per minute, and time taken was 2 hours. Next, we go to the result part. The 4 bottles of 1 liter, which are A, B, C, D were labeled in with different concentration of nutrients and were monitored for 16 days. The color has also been observed every 5 days. At day 0, the color of all the photobioreactor bottles are similar as the same amount of the seed. At day 5, the color of the bottle A, B, and D still similar while bottle C changed a bit. At day 10, the color of A and D become yellowish while bottle B and C turn darker. At day 15, all the color in the bottles are changed. The bottle D from yellowish at day 10 become deep green at day 15. This can be stated that if the color turns deep, there is rapid growth occur. From the graph plotted, the optical density is measured by using UV spectrum photometer for 16 days. The graph shows that the optimum growth for Chlorella vulgaris at day 16 is occupied by 50 ml of nutrients. The result of the elemental analyzer has tabled. The percentage of the composition of elemental analyzer results for dry biomass of Chlorella vulgaris turns out to be lower than the value of literature review. Some error might occur during the drying process. Maybe it's the overburnt because leave it overnight. In conclusion, the optimum condition is the growth medium with the concentration of 40 ml nutrients and the percentage of carbon content in Chlorella vulgaris is 3.15%. Lastly, the recommendation for the future study is there should be more optimization of pH. Study the different types of nutrient which use other than compost fertilizer, and study the intensity of light, and the cultivation should be go under in outdoor or indoor polluted environment.